I'll be teaching you the rate law in chemical kinetics, how to write expression for rate law and other calculations involving rate law of a chemical reaction. Remember, there are two ways of expressing the rate law of a reaction. It's either you express with respect to concentration and time, or you express with respect to rates of a reaction and concentration. This is what I mean. The first method of rate law expression is the one we call the differential method. In the differential method, it is the expression that shows the relationship between the rate of a chemical reaction and the concentration. Remember, when we say rate of a reaction, it simply means the speed at which the chemical reaction takes place. And the differential expression, we have the differential method and the integrated expression. We have the differential rate law and integrated rate law. When you talk about the differential rate law, you talk about the relationship between the rate of a chemical reaction and the concentration. So, in the differential rate law expression, we say that rate of a reaction is equal to K, which we call the rate constant, multiplied by the concentration. I'm using A as my reactant. And you know in chemistry, this square bracket simply stands for concentration. So here, this equation means rate is equal to K, which we call the rate constant, multiplied by concentration of A. We are assuming that our reactant is A. This is what you call the differential rate law expression. Don't forget this. Differential expression is the expression that shows the relationship between the rate of a chemical reaction and the concentration. K here is called the rate constant of the reaction. In the integrated expression, we talk about the relationship between the concentration and time. How concentration depends on time. Remember, in chemical kinetics, you are meant to understand that as a chemical reaction goes on, the concentration of the reactant keeps decreasing as time goes on, while the concentration of the product continues to increase as time goes on. So the integrated rate law expression tells us the relationship between concentration and time. For instance, if I'm talking about a zero order reaction where I want to show the relationship between concentration and time of the reaction, I will say for a zero order that my initial concentration, which we call A naught, minus my final concentration, which we call AT. A, that is concentration at a given time. This is original concentration, is equal to KT. That is rate constant multiplied by time. This formula that shows the relationship between concentration and time is the one we call the integrated rate law expression. While the one that shows the relationship between rate of a reaction and concentration is the one we call the differential rate law expression. Now, we are going to look at what we call reaction order. We are going to look at reaction order of a chemical reaction. The order of a chemical reaction is defined as the exponent of the concentration. That is the power given to the concentration in the rate law expression the power of the concentration is what you call the reaction order. For instance, if I have a rate law expression which is written as rate of chemical reaction equals rate constant times concentration raised to power 1. If I have a differential equation like this, why do I call this differential equation? Because it is an equation that gives relationship between rate and concentration. Remember, the formula that shows you the relationship between rate of a reaction and its concentration, such a formula is known as the differential rate law expression. Now, if I have a rate law expression like this, where rate is equal to rate constant multiplied by concentration to the power of 1. Someone asked me, what's the order of this reaction? Note this, the order of a chemical reaction is the exponent of the concentration. Exponent means the power. Here, in this rate law expression, the power of the concentration, here is my concentration A. The power of this concentration is 1. Therefore, since the power is 1, the order of this reaction is equal to 1. And 1 simply means first order. If I have the rate equation given to me as concentration raised to power 2, this simply means that my order for this reaction is what? 2. Remember, the order of a reaction is the exponent of the concentration. That is the power of the concentration. Now, what if a rate expression is given as rate equals rate constant, and you are asked, what is the order of this reaction? All you need to ask yourself is, what is the power of concentration in this expression? Because your order is the power of the concentration. So since concentration is not appearing here, I will write this equation by saying that rate is equal to rate constant multiplied by concentration to the power of 0. Remember, anything raised to the power of 0 is equal to 1. So it simply means that A raised to power 0, that this concentration raised to power 0, the whole of this is equal to 1. And 1 multiplied by K is K. So this and this are the same. When it is given to you without giving you the concentration, it simply means it has a power of 0. Because A raised to power 0 is 1, and 1 times K is K. So this and this are the same. And because this and this are the same, it simply means that the order for this reaction is equal to 0. That is 0 order reaction. Now, we are going to proceed to learning how to find the order of chemical reactions when they are not given to you, when they are represented with letters. How do you find them? You should note this. If I have a chemical reaction, for instance, given to me as 3A plus 2B producing C plus 4D, for instance, if I have a chemical reaction like this, and the rate of the reaction is given as K multiplied by concentration of A times concentration of B. I'm using A and B, the reactants, the concentration of A times the concentration of B. If I have only one of the reactants here, I will use only A, like this. But I have two of them, so I'm using the 2. Now, you should know that the power, the exponent of the concentration is not the number of moles in the balanced equation. No. The powers here are gotten experimentally. Simply means that an equation can be given to you, or a table, a data can be given to you, and the rate is given to you, while the powers here will be given as x and y, and you will be asked to find the values of x and y. And by the time you find values of x and y, you'll be able to tell us the order of the reaction.